Hello everyone, it's me, Professor Aaron Albert, here again with Lesson 12. Let's learn some econ. So today's goal is to begin talking about consumer surplus, compensating variation, and equivalent variation. So today is going to be the first lesson on this. We're just going to find CV and EV, i.e. compensating variation and equivalent variation, using graphs. And then we're going to show how you go about solving it numerically. We'll finish that next time. So in order to understand why CV and EV are important, we should take a moment to remember what consumer surplus is. So here I have sort of a typical consumer demand diagram. We have Q, demanded, P, set by the market. And we should take a moment to ask ourselves, given any P in this diagram, how can we find utility levels? Second, let's let P be this. Given that P, what is consumer surplus? Also, given this P, how much did consumers spend on the goods they bought? So, first thing we should note that this demand function tells us how much consumers are willing to spend at any given for any given quantity. So you could map price into quantity and say, oh, for this many dollars I demand this many, or if I'm going to buy this many units, I would accept this price. So utility then will be given by the area under this curve. However, working against our utility is how much we have to pay. So let's say that our P is set on the diagram like this. Well, at this price, we'd intersect demand and note that we demand Q1 units. In total, from these units, we would have been willing to pay the entire area under this curve to the left of Q1. We ended up paying P1 for each unit. What's the total amount we spent? Well, that's P1 times Q1. We get Q1 units at P1 apiece. Now you'll note that we paid this rectangle, and we get utils from this rectangle plus this triangle. Therefore, this triangle is our consumer surplus, namely the amount we would have paid and we didn't have to. It's good. The next question is, well, what happens to the consumer surplus when the price increases? Let's suppose that the price went from P1 to some P2. On your own, determine what happened to our consumer surplus. So you'll note two things happened first. First, as price went from P1 to P2, we demand less product. Second, we're buying fewer products, also at a higher price. So the amount we've paid now becomes this rectangle, and our consumer surplus becomes this. You'll note that this is lost consumer surplus, right? This triangle reflects goods that are no longer purchased, i.e. we've gone from this Q to some lower Q, and this is lost because we're now paying this for the more expensive products. It's important to remember this because this is what we're trying to do when we're solving CV-EV problems. The important thing is that CV-EV must be done because so far we've been working mostly in a quote-unquote too-good world. So these types of changes are very simple because there's one good. What happens when price increases in a one-good world? We buy less of that good. What happens in a two-good world? Remember back from our last two lessons. What happens during a price change if you can consume two goods? Well, two things happen. First, you're going to buy less stuff, right? There's the income effect. When a price goes up, normally, that means you have less money to go around because things are comparatively more expensive. But the whole consideration is complicated by the fact that we also are going to buy different things. So we can't just say, oh, we're worse off because we have less money. Well, we have less money and we also buy different stuff, and that has to be accounted for. So that's why we have to go through this exercise to find CV-EV if we want to determine how much better or worse we are off after some sort of price change. So let's start off with a silly example with CDs and DVDs. Suppose we start at point A you'll note that this is some budget associated with some indifference curve, and that between A and B, the price of CDs has gone down. We know that because the maximum quantity of CDs we can buy, if we buy only CDs, has gone up, and there's been no change in the intercept for DVDs. So the question here we want to know is, well, how happy are we at point A and B? How do we compare these? We know we're better off at B. Why is that? Well, we must be better off at B because this is northeast of A. But how much better off? Well, we could say that this is higher utils than this, but nobody, including me, would actually know how to quote somebody utils, right? Utils are a weird made-up thing. So what we try to find here, what we try to do with CV and EV, is determine how many dollars would it take to make me as happy as I am at B without changing the prices. That is, how many dollars of income could you give someone at A to make them as happy as they are at B? There are two ways to compare the dollar difference in happiness between A and B. One is CV, one is EV. This difference between these two is incredibly subtle, and you should be, at the end of these lessons, well versed in how to find both, but I will never make you answer a quiz or test problem that's trying to figure out which is which, right? I will ask you to find CV or EV many times, and I'll tell you which one I mean, because remembering which is silly and a waste of your brain power. So if we had a whiteboard behind me, I would write these in big letters on the board, but instead I'll leave this, write this down in your notes somewhere for reference. We'll need this soon. Compensating variation is the dollars that someone would have to pay to fully compensate you after a price has increased or decreased. So imagine you're at A, the world has changed to B. Well, how many dollars does somebody have to take away from you to make it such that you're as happy as you were to start with? Note, compensating variation uses our new prices and the original utility level. And if what I mean by this is unclear, stand by. You'll see in a minute on a graph. The equivalent variation is the dollars that someone would give or take away from you before a price change in order to make you indifferent between that price change happening. This, importantly, uses old price lines and the new utility level. And again, you'll note that these two things sound incredibly similar, right? They're both describing how many dollars better or worse I am after a price change. So imagine a price goes up. Compensating variation is how many dollars must you give me after the price goes up for me to be as happy as I was before the price went up. Equivalent variation is how many dollars I would pay someone such that they do not raise the price. These numbers will, for the most part, not be identical, but they're going to go in the same direction, right? If I am worse off after a price change, one, you'd have to give me money to make me as happy as I were before, and two, I would pay you money to not do that. So let's see how these two similar concepts are, in fact, slightly different. So this graph we're going to use first to find CV, and then we're going to use the same graph to find EV, so we're going to use all these dots. So CV, I'm going to tell you, is going to be the vertical distance, i.e. the difference in dollars between C and between B. You'll note that C is defined as the optimal bundle on this dotted purple line, and B is defined as the optimal bundle on this solid purple line. And you'll note that this purple line and this purple line are directly comparable in dollar terms because they're at the same slope, right? I could take this purple line, give you some extra dollars, and then vertically displace it to become this. It's a parallel shift. So in order to find a CV, you must perform the following. First, find the original bundle and utility level associated with it. Since we start with the blue line, i.e. point A, you'll note that's associated with this indifference curve. So that means we start at this utility level. Then we're going to note that the price level has changed. We've gone from blue line to purple line. Our question is, well, how many dollars would I have to spend on this purple line to reach my original utility curve? So I start at A, I note that A is associated with the utility level of A, C, and every other point on this curve. Then the price changes to B, and I note that I would need some additional dollars from B to reach some point like C that is on this indifference curve, but also tangent to this indifference curve on a budget line that is parallel. So to work through this, let's find the relevant points. First off, in your own notes, find the original bundle that is optimal before the price change and what utility level is associated with that. Then change the price and find what utility level you're at now. Then, using the new prices, find the compensated budget line like we did during a price change, i.e. the budget line that uses the new prices and the original utility level. The pace between the new budget line that we've drawn that's compensated and the original budget line, that is your CV. So to be clear, we start at A. A is indifferent to C. At the new prices, we can afford B or D. The compensated demand we could find is associated with point C. The dollars between C and B is our CV. So that was how we found CV. Now let's do the same exercise to find EV. In order to find EV, we must perform the following. First, assume we start at point A. The price changes to the purple line. We consume point B. What is, graphically, my original utility level, and where was my original budget? Then, after the price change, what is my new utility level? Using parts 1 and 2, draw the compensated budget. That is the budget that would get me the new utility level using the original prices. The space between this and the original budget is your EV. And we can do this just like we do the CV, but backwards. First, you'll note we start at A. A is indifferent to C. Next, we'll note that at the new price levels, our optimal bundle is D. D is indifferent to B. Note that I can create point D by trying to find a point on the new utility level that is tangent to my original budget. The distance between A and D is my CV. So CV is this distance, EV is this distance, CV is this distance. And although they look similar, mathematically they will often not be exactly the same. So we should take a note to see exactly what we need to do to find this mathematically. So let's start with CV. Let's say we had some budget and some indifference curve. How would I find B? Right, I have a purple line, which is my new budget, and I have my indifference curves. What is B? Well, B looks to be the new optimal bundle. What is C? Well, C would be some sort of expenditure minimization subject to my original utility level at the new prices. This is basically how you go through to find CV. In order to find CV, we need to find C and B. To find C, first, get your optimal Q1 and Q2 by performing the relevant utility maximization. Using Q1 and Q2, you can find your original maximized utility. We'll call that U star. Then, our next goal is to find the dollars required to find this U star at the new prices. To do this, we'll perform a expenditure minimization subject to the U star we originally had before the price changed, but do it at the new prices. Doing this, we'll find some Q1, Q2 prime, just these new solutions to this expenditure minimization. And if we take those Q1s and Q2s and multiply them times prices, we'll get the total expenditure. Call that expenditure E prime. You'll note then that how much we had to spend originally to get our original util is just going to be Y, and how much we have to spend at the new prices to get our original util, we'll call that E prime. The difference between those is the compensating variation. Next question is, well, how could I find my equivalent variation mathematically? The process is largely the same. We're just doing a utility maximization subject to a different budget and an expenditure minimization subject to a different budget. So first thing we need to do is figure out our new maximum utility doing utility maximization. To do that, figure out your new budget after the price change, and then find your optimal Q1, Q2 prime given the new prices and your budget that's given to you. Then, given Q1 and Q2 prime, i.e. the optimal quantities at the new prices, find what I'll call U prime star, i.e. your new maximum utility that you can reach after a price has changed. The next task then is to find how many dollars it's required to get this U bar prime at the original prices. To do that, find some Q1, Q2, which get you this U prime star for the least amount of money. Then, using these found Q1, Q2 values, times them by your original prices, and we'll get an expenditure we'll call E. Then, Y minus E would be your, sorry, this is a typo, EV. So, to bring this home once more, in order to find compensating variation, we're trying to find the dollars that would fully compensate an individual after a price increase or decrease back to their original utility level. We need to find the expenditure associated with your original prices and then track that from the expenditure it takes to get that utility at the new prices. For equivalent variation, we need the dollars that it takes to get the individual indifferent to a change before it's happened. We would need to find the expenditure at the original prices associated with the new utility minus the expenditure at the new prices associated with the original utility. The best way to do this is through practice, and we'll do really easy practice problems first. The reason they're easy is because we're going to do complements, which doesn't require a ton of algebra. So let's let U equal the min of Q1, Q2, let our prices and income be given as thus, and suppose that P1 increases from 1 to 2. And our question is, what is the compensating variation? Before we start, either remember or flip back through your notes. What are the steps? How do we find CV? Well, the first thing we need to do is find U star, i.e. our original maximum utility possible. The second thing we want to do is determine how many dollars it would take me to reach the original utility at the new prices. Well, how many utils can I get at the original prices with my original dollar budget? How do I solve perfect complements? Hopefully you'll remember that I must set Q1 equal to Q2, and also I know that Q1 plus 2Q2 must equal 10. So if I buy 1 Q1 and 1 Q2, that gets me 1 util. That costs me $3. So it looks like my maximum utility is going to equal 10 out of 3. How many dollars does it take to get 10 out of 3 utils at the new prices? Well, the cheapest way to get an individual util at any price, since this is perfect complements, is going to be to buy one of each. So now each util costs me $4, and I need 10 out of 3 utils times $4. It looks like this will cost me 40 out of $3. You'll note that originally it cost me 10 out of $3. Sorry, $10, because my Y was 10. So the difference between 10 and 40 out of 3 must be my compensating variation. Go through the same steps and find yourself EV and see how it compares to your CV. Then, try to find the CV and EV associated with this other special case. Here we have perfect substitutes. Let your utility be given by Q1 plus Q2. Again, let P1 be 1, P2 be 2, and Y be 10. And suppose your P1 increases from $1 per unit to $3 per unit. Find the CV, find the EV, and see how different they are. Good luck. Let me know how you do. See you next time. Bye.